So far for the XOR function, we have learned the weight in ad hoc fashion. So we were able to, just by tweaking the value of the sigmoid function, we could find that the weights on the connections in the neural network. So you could imagine that for larger networks with more complicated functions, it's not possible to do to tweak the weights this way. We need a method, and one of the methods to do it is called backpropagation algorithm that actually allows us to learn the weights on the network using gradient descent. So let me first mention that we are talking here about what we call feed-forward neural networks as opposed to recurrent networks, since we have no connections that actually loop. So we're going to go with the networks that actually are simple, going from left to right with the inputs on the left and the outputs on the right. So the learning task here is to learn the weights for a multi-layer network and to use the backpropagation method that stands actually for backward propagations of errors. So we'll see in a bit what this means. So given a network with a fixed architecture, so we know what are the neurons in the connections, use gradient descent to minimize the squared error between the network output value, which we call O, and the ground truth Y, which means the labels, so the labels of the example. So we suppose that we have multiple output K. This is to make it general. And the challenge is actually to search for all possible weight values for all neurons in the network. And this is actually means that we're going to sift through possible combinations of weights that actually lead to a good learning of the examples and their class labels. To clarify these concepts of feed-forward and backpropagation, let me give you an example of a fully connected neural network with one hidden layer, one input layer, and one output layer. So observe here that this is a fully connected network in which we have any neuron is connected to all the neurons in the next layer. So there are also weights on the different connections. So each connection will be weighted by some wij between the neuron I and neuron j. So also called units. So given an example, let's call it E, a pair x and y, where x is, remember, this is the feature vector, and y is the label. What we are going to do is to feed the network your x, right? So I'm going to put the x, which is the feature values, into the neurons as input to the network, okay? So these values will be moved forward to the right from connection to connection using the weights. So each neuron, remember, has some activation function that actually is this weighted sum of the neurons as input that is cast within some function, sigmoid or other. And the information at each neuron is then calculated by taking the inputs of this neuron weighted by the W's. And then you could push the information forward until you got an answer. Let's call it O. So for this example, we're going to get an OE. This is the predicted outcome or the function that actually this network is computing for the example. Observe here that actually this is our f of x actually, right, for the example E. So observe here that actually we can easily compare the outcome that we are getting to the true label. The true label is not used for training. So just comparing, given the current state of the weights, we are going to compare what the network is telling us as the predicted value for the label as compared to the true label y. So we're going to compare these two, and if there is an error, how we happen to fix the weights is to do what we call backpropagations. I'm gonna move back this information about the network making a mistake backward in the network. So as I go back and fix the weights until I get the right answer I'm looking for. Okay? So the backpropagation means that given the true label and given the output label, we're going to compare them and go back if necessary to fix the weights in the network. So we're going to backpropagate the information and start over until there is convergence and the network is classifying this example properly. Let's formalize the concept of backpropagation by a set of backpropagation rules. So first of all, to remain in the general case, we are going to consider k outputs, which means that on the output layer we have k possible neurons or units. This come in handy if we have a multi-class classification, let's say the digits between 0 and 9. For an example E defined by the pair xy, x being the feature values and y being the label, The error on training the example E is the sum over all the output neurons in the network. In other words, we're going to consider the error of the example E given a configuration of weights is the sum of all the mistakes that the network is making as compared to the true label squared, and we add half to make the calculations easy later on. So this is, you recognize this, this loss function. Remember, when we use the gradient descent, we iterate through all the training examples one at a time by descending the gradients to actually of the errors, so as we can update the weights. So in this example, in this case, the delta of Wij, so Wij is the weight between the neuron I and the neuron J, would be minus alpha, where alpha is actually some learning rates, just as we did in the gradient descent for linear regression, with the derivative of the error that we have on each example with respect to the partial derivative of E with respect to Wij, which is the weight between I and J. So I'm going to descend the gradient another time, but this time we're going to consider the error for each example and try to find the better ways by decreasing those weights by a delta Wij. So let's adopt the following notations. We're going to call Xij the ith input to neuron J, which means that this is what's coming out from the ith neuron going to the jth neuron and through using the weights and the in between. So the weight Wij will be the weight associated with the ith input to neuron J. We're going to call Zj the weighted sum of the Xj, Wij for all I. Okay, so this represents actually the weighted sum of the outputs for neuron J. Oj represents the output computed by neuron J. It could be at the end, it could be in the middle in the hidden layers. G is our sigmoid function we have defined earlier to use to squash the input, the weighted sum. The outputs are the set of neurons in the output layer. And we are going to call successors of J, or suc of J, the set of neurons whose immediate inputs include the output of neuron J. To clarify these notations, let's just put them on the network, the previous network that is fully connected with one hidden layer in the middle. Suppose our jth unit or jth neuron is this neuron here that actually gets its input from this neuron here, this one, and this one. So any of these neurons is actually possibly an I neuron getting given its output to the neuron J. Okay. Remember the connections are Wij, which means that what's coming out of I is being weighted by Wij and contribute into the weighted sum Wij Xj for all I. So we're going to take the output of each of the neurons going into the J, weighted by Wij, to get the function that we call Z of J. Okay, this is G of Z. So remember, we are going to use a squashing function or a threshold function or any other kind of functions to squash this between, make a smooth function to squash these values between 0 and 1 or minus 1 and plus 1. So we're going to apply a G of Zi. And remember, G of Zi is the sigmoid function. Okay, so this will actually constitute what we call the output of the neuron J. So at this level, we are talking here about the hidden layer, but J could be actually this neuron here. And in this case, we're going to consider these three neurons going into J. And the principle is the same. We're going to get an O of J, but we're going to weight Z of J would be the weighted sum of these three neurons that we put into the logistic function, and we get O of J, which is G of Z of J input, the weighted sum of all the inputs. The only difference between neurons in this layer and the output neurons is that there is no more neurons after that. However, for this one, they have a set of, each one of these neurons has a set of successors. So for example, neuron J has only one successor, which is also the successor of this neuron and this neuron. If we have, for example, multiple neurons in the output layer, then we would have the successors of J would be these two neurons here. This would be constituting the successor of J.